Welcome to our quantum deep dive. Today we're really digging into how something as fundamental as, quantum mechanics might just reshape the future of data. And our map for this journey is a really insightful essay by Yurgo Shinepot called Quantum-Optimized Data Preprocessing for AI and Big Data. We hear it all the time, AI and big data are changing everything. But the fuel for these engines is data, and the quality of that data is just critical, right? Trying to process these huge, messy data sets with the old methods, it feels, like being stuck in gridlock traffic on a superhighway. Slow, really inefficient.
That's a great analogy. Yeah, raw data is just inherently messy. It's noisy, full of redundancies, often totally unstructured. Think of like a giant library where none of the books are sorted or cataloged. Before you can find anything useful or, train a smart AI, you've got to clean it up, sort it, make it manageable. And yeah, traditional methods are really starting to creak under the strain. The volume is just immense. Preprocessing isn't just nice to have, it's essential.
Okay, so let's unpack that. Our mission here is to figure out why the old ways are hitting this wall, and, more excitingly, where quantum computing comes in as this potential game changer. We'll touch on the basic quantum ideas, look at some specific quantum tricks for data prep, and then, get real about what's possible now and what's still down the road. Prepare for maybe a few mind-bending moments.
Yeah.
So this data deluge, we're drowning in it. What are the actual pain points Shinepot points out? Why are classical methods struggling so much with prepping data for AI?
Yeah, it really boils down to a handful of key challenges. First off, there's scalability. Many algorithms we rely on, things like principal component analysis or k-means clustering for grouping data. Their computational needs just explode exponentially as the data gets bigger. They just don't scale well at all when you hit genuinely massive data sets.
Right, so what takes minutes today could take centuries tomorrow with more data.
Exactly, and linked to that is the sheer computational effort. Things like inverting huge matrices or running optimization routines over and over for reducing dimensions or finding clusters. These tasks don't just take time, they demand enormous amounts of processing power and memory. You might not even have the hardware to run them.
Okay, so it's not just slow, it might be impossible.
It can be. And then there's information loss. This is a subtle but really important one. Sometimes, to make the data manageable, classical methods have to simplify things, maybe drop certain data points or features. The risk is you end up throwing away something crucial, some important detail or pattern, and that can lead to biased AI models, or just models that aren't as accurate as they could be.
Okay, so feeding messy, poorly prepped data is bad. Our old tools are struggling. What's the fundamentally different way forward? This is where quantum computing enters the picture, right?
Yeah.
And it sounds, radically different. Before we get into the algorithms, let's cover the basics. For anyone listening who hears quantum and thinks, physics lecture, what are the absolute need-to-know concepts? Why is this a whole new ballgame for computation?
Right. Let's break it down. The absolute core ideas you need are qubits, superposition, and entanglement. So, qubits. Unlike a classical bit, which is strictly a 0 or a 1, a qubit, it can be 0, it can be 1, or it can be in a combination of both states at the same time.
Both at once.
Both at once. Think of it less like an on-off switch and more like a dimmer switch that can be simultaneously at, say, 30% brightness and 70% brightness. This ability to hold multiple values simultaneously is what allows for this massive parallelism.
Okay, so that's the qubit. What about superposition?
Superposition is basically that state of being both 0 and 1, or some combination. Imagine spinning a coin. While it's in the air before it lands, it's neither heads nor tails. It's in a superposition of both possibilities. Quantum operations, like something called a Hadamard gate, can put a qubit into this state, letting it explore multiple possibilities simultaneously.
Wild. And the last one, entanglement. That sounds even stranger.
It is pretty strange. Entanglement is when two or more qubits become linked in this really deep way. Their fates are intertwined no matter how far apart they are. If you measure the state of one entangled qubit, say, you find it's a 0, you instantly know the state of its partner, even if it's across the galaxy.
Instantly? Like faster than light?
Well, the information about the state is revealed instantly upon measurement, but it doesn't let you send messages faster than light. It's more like correlated fates. It's this weird non-local connection that Einstein famously calls spooky action at a distance. And it's absolutely critical for many quantum algorithms and things like quantum cryptography.
Okay, my brain hurts a little, but I think I get the basic ingredients. Qubits hold more info, superposition lets them explore options, entanglement links them.
Yeah.
How do we actually control this stuff? What are the quantum computer's instructions?
We control them using quantum gates and circuits. Think of these like the logic gates, AND, or not near classical computer, but designed for qubits. You have gates like the Hadamard gate, which we mentioned to create superposition. You have Pauli gates for rotations, and things like the CNOT gate, which is crucial for creating entanglement between two qubits. A quantum circuit is just a sequence of these gates applied to qubits in a specific order to perform a calculation.
Got it. Gates are the operations, circuits are the sequence. And what about the machines themselves? Schneppat's essay mentions two main types.
That's right. Two main models are important here. First, gate-based quantum computers. These are kind of the general-purpose quantum computers. They run algorithms as sequences of these quantum gates, much like classical computers run instructions. Shor's algorithm for factoring large numbers, that runs on a gate-based model, and it promises that exponential speedup, potentially breaking modern encryption.
Okay, the universal type. And the other?
The other type is quantum annealers. These are more specialized. They're built specifically for tackling optimization problems. Instead of running gates, they use a quantum phenomenon called tunneling to find the lowest energy state of a complex system, which often corresponds to the best solution for an optimization problem. D-Wave systems is the big name here. They formulate problems as QUBO's quadratic unconstrained binary optimization problems. They aren't universal computers, but for specific tasks like clustering or maybe feature selection and data preprocessing, they could be really useful.
Okay, so we have the quantum toolkit, qubits, superposition, entanglement, gates, and different types of machines. Now, let's connect this back to our data problem. How does all this quantum magic actually help with pre-processing all that messy big data? What algorithms are making waves?
All right, this is where the potential really starts to shine. Quantum algorithms offer the promise of significant speedups for some of the really computationally heavy parts of data preprocessing. One big area is quantum machine learning, QML. It's a broad field, but Schneppat highlights a few key approaches. You've got quantum subroutines speeding up classical algorithms like using quantum techniques for linear algebra, which is everywhere in ML. Then there are hybrid models, where maybe the quantum computer does some complex feature transformation, and a classical computer handles the rest of the training, and then fully quantum models. A really key algorithm here is the Haro-Hasidim-Lloyd algorithm, or HHL.
HHL, what does that do?
It's designed to solve systems of linear equations. Classically, this can be really time-consuming for large systems, often scaling cubically with the size, n cubed. HHL offers the potential for an exponential speedup, potentially solving these systems in logarithmic time, log n. That's a massive difference.
Wow, okay. Solving linear equations faster would impact tons of data science tasks. What else?
Then there's quantum principal component analysis, QPCA. Classical PCA is a workhorse for dimensionality reduction, finding the most important patterns or features in complex data. But again, it gets very slow, often n cubed, for large data sets. QPCA, developed by Lloyd and others back in 2014, uses techniques like quantum phase estimation. The upshot is it can potentially extract these principal components in logarithmic time, again, log n.
So exponentially faster dimension reduction. That sounds incredibly useful for making sense of huge data sets.
Exactly, finding the signal in the noise much faster. Then for grouping similar data points, there's quantum k-means clustering. Classical k-means is widely used, but its runtime typically depends on the number of data points n, dimensions d, and clusters k. Quantum k-means algorithms aim for a polynomial speedup, potentially running faster by a factor related to the square root of n. They use clever tricks like quantum distance estimation and amplitude amplification.
A polynomial speedup isn't exponential, but still potentially a big improvement for large n, right?
Absolutely. It could still make a huge difference for very large data sets. And finally, related to QPCA is the broader area of quantum feature selection and dimensionality reduction. Picking the right features is vital for good AI models, but finding them can be slow. Quantum approaches like quantum support vector machines, QSVM, leverage quantum methods for calculations. And hybrid approaches look promising too, maybe using quantum algorithms like quantum Fourier transform for faster feature extraction, then feeding those features into a classical ML model.
So if you're someone wrestling with these massive, unwieldy data sets every day, what's the bottom line? It feels like this offers a path to finding insights that are just completely hidden right now because we can't process the data fast enough.
That's exactly the promise. It's about unlocking the potential hidden within the sheer scale and complexity of modern data, processing information and uncovering patterns far more efficiently, enabling AI breakthroughs that are currently bottlenecked simply by computation.
Okay, the potential is definitely exciting, revolutionary even. But let's bring it back down to earth. How close are we, really? What are the practical roadblocks mentioned in the essay to actually using these quantum algorithms today?
Right, the reality check. There are definitely significant challenges moving from theory to practice, but also real progress. On the software side, things are actually looking pretty good. We have powerful frameworks. IBM's Qiskit is great for gate-based programming, letting you simulate or run on their real hardware. Penny Lane from Xanadu is really focused on this hybrid QML approach, integrating with classical tools like PyTorch or TensorFlow, and Google has Cirq, optimized for their quantum hardware. So the tools for researchers to build and experiment are there.
So the software tools exist. What about the hardware itself? Simulation versus reality.
Yeah, that's where the gap is wider. Most complex algorithm testing still happens on simulators. These classical computers can simulate maybe up to 30, 40, perhaps 50 qubits perfectly without errors. But real quantum hardware, while improving incredibly fast, is still, quite limited. We're talking maybe 50 to a few hundred qubits from leading players like IBM and Google. And crucially, these real qubits are noisy and error-prone.
Noisy and error-prone. That sounds like a major hurdle.
It's arguably the major hurdle. This brings us to the big technical challenges. The biggest is error correction and decoherence. Qubits are incredibly sensitive. Any tiny interaction with their environment, heat, vibration, stray fields, can make them lose their quantum state. That's decoherence. To combat this, you need quantum error correction. But this is super resource intensive. It might take hundreds, maybe thousands of these fragile physical qubits just to create one stable, reliable, logical qubit.
Wow. Thousands to one. That scales up the requirements massively.
Hugely. Which leads to the next challenge, hardware limitations and scalability. For truly fault-tolerant quantum computers that can run algorithms like Shor's on meaningful problems or handle massive QPCA, we likely need millions of stable, well-connected logical qubits. Building such machines is an immense engineering challenge. It involves things like extreme cryogenic cooling, down near absolute zero, and complex manufacturing to couple all these qubits together reliably. The roadmaps are ambitious, but getting to millions of logical qubits is still a long way off.
Okay, so given these hardware limits and the noise issue, it begs the question, when does quantum actually beat classical? It's clearly not for everything.
Definitely not. You have to pick your battles. Quantum really shines where you get those exponential speedups. Things like factoring with Shor's algorithm or solving those linear systems with HHL. That's where the potential for truly transformative speedups lies. Then you have problems where quantum offers polynomial speedups, like quantum k-means or potentially QPCA in some scenarios. This is still valuable, especially for very large n, but maybe not as game-changing as exponential. But for straightforward tasks like basic arithmetic or running simple code, your laptop is way faster and more reliable. Classical computers aren't going away.
So it sounds like the immediate future, maybe even the medium-term future, isn't about replacing classical computers, but augmenting them. Is a hybrid approach the way forward for now?
Exactly. That's the consensus and what Schnepat's essay points towards too. Hybrid approaches are really key right now. Let the quantum computer do what it's uniquely good at, those specific complex calculations that are intractable classically. Maybe it's tackling a hard optimization step in feature selection or exploring complex correlations in the data. Then you hand the results back to the classical computer to do the rest, the data management, the bulk of the model training, the user interface, all that stuff. This lets us potentially get some quantum advantage, even with the noisy intermediate scale quantum NISQ hardware we have today and in the near future.
Well, this has been absolutely fascinating. We've gone from the traffic jams of classical data processing through the weird and wonderful world of qubits and entanglement to seeing how these ideas could actually speed up tasks like finding patterns and cleaning up data.
It's a field moving incredibly quickly. Yes, it's still early days in many respects, and those hardware challenges are real, but the progress on all fronts, hardware, software, algorithms, is undeniable. Fully fault-tolerant quantum computers might still be many years out, but these hybrid approaches are already starting to explore that quantum advantage. They're building the bridge to more powerful AI and big data analysis.
And connecting it back to the big picture, this isn't just about faster spreadsheets, is it? It's about potentially unlocking breakthroughs in science, medicine, materials, things we can barely imagine now, all because we can finally make sense of the data. Though, yeah, cracking those hardware and error correction nuts is crucial.
That's the ultimate goal. Absolutely.
So for you listening, the big takeaway here, I think, is that quantum computing, especially for data, isn't just sci-fi anymore. It's an active area of research and development with the potential to seriously shake things up. Keep an eye on it. And that wraps up our deep dive for today, guided by that excellent essay from Jörg O. Schnepat. If you're keen to learn more, you can find further details and resources over at schnepat.de. Until next time, keep exploring.